excuse me, and wait for.
I don't ever slow up, no I don't take shit, I got no love.
Here are three of the most common design mistakes I see engineers making. First is over-tolerancing. Engineers often specify tolerances that are tighter than necessary. A plus minus 100th of a millimeter tolerance on a non-critical hole doesn't improve performance, but it dramatically increases cost and machining time. Tight tolerances should only exist where they truly matter. Second is overcomplicating your geometry. Features that look cool in CAD, like tiny undercuts or sharp internal corners, can slow machining, require special tooling, or increase scrap. Simplifying these early saves hours on the shop floor and reduces costs. Third is designing without knowing what your supplier can actually do. Designing intricate internal channels for injection molded parts, for example, might look perfect on paper, but can require specialized tooling, multi-piece molds, or result in unexpected delays. Many engineers find out too late during production, which is frustrating and costly. This is why I rely on Giga.io, who is, as an engineer, I'm always working on the computer, whether it's CADing or programming. Eye fatigue and back. Here's how I prepare for my mechanical engineering interview. I solved 2,138 mechanical engineering practice problems. Memorize all of the answers. Read the machinery's handbook 5 times. After countless brutal late nights completing projects and studying for exams, you graduate with a mechanical engineering degree. All your hard work paid off. University helped you master key engineering knowledge and skills in thermodynamics, materials, fluid dynamics, mathematics, mechanical design, and more. You land your first mechanical engineering job and enter industry with high hopes and dreams. However, you realize something quickly. University prepared you to think and analyze problems, but it failed to prepare you for the moment a machinist calls you at 4 p.m. to tell you that the part you spent 3 weeks designing is physically unmachinable. So in this video, we'll break down all of the specific skills you need to accelerate your career, bridge that gap to succeed in industry, and stand out as a mechanical engineer who can design and deliver quality hardware products. I'm also excited to share a game-changing tool, Giga.io, that's completely changed the way I design, make parts, and collaborate with manufacturers, and has made going from prototyping to production a breeze. So at number 1, and arguably the most important, is design for manufacturing and assembly, or DFMA. In university, DFMA is often introduced at a conceptual level, like reducing part count, avoiding sharp corners, and adding draft angles. But real-world product design is constrained by things like capital investment, tooling access, cycle time, scrap rate, and supplier capability. A part that works is not enough. It must also scale. A CNC mill is a 3 or 5 axis machine with specific physical limits. DFM is about knowing those limits before you start detailed design. The biggest mistake is ignoring tool aspect ratios. A 2mm end mill can only cut so deep before it starts to walk, chatter, or just snap. If you design a deep, narrow pocket with sharp internal corners, you're asking for a part part that's either impossible to make or incredibly expensive because it requires electrical discharge machining or a custom long reach tool. You need to design your internal radii to be slightly larger than the radius of the tool you want the manufacturer to use. Seemingly minor geometry decisions can double part cost. Injection molding introduces its own constraints. Draft angles are required for ejection, wall thickness uniformity controls sink and warpage, and rib geometry affects stiffness and cooling time. Design for assembly or DFA principles are equally important. Reducing fastener count reduces torque operations and cycle time. These decisions affect yield and throughput when tens of thousands or millions of units are made. I've seen designs where a mechanical engineer put a bolt in a spot where you literally couldn't fit a socket, let alone a human hand. You have to plan the assembly sequence. Can you reach the fasteners? Can a technician see what they're doing? If you need a specialty tool to put two brackets together, you've increased the labor cost and the likelihood of assembly errors. Use a poka-yoke approach by designing parts so they physically cannot be put together incorrectly with things like asymmetric bolt patterns or locating pins. DFMA at its core is about aligning geometry with each manufacturing process's constraints and physical principles. That alignment is rarely taught in university, but it's one of the top skills companies like Apple and Tesla look for in candidates because it directly impacts a company's bottom line. Now, the second skill is often overlooked and relates to DFMA, and that's designing within manufacturing capability. Every manufacturing process has capability limits. When you send a drawing to a vendor, you're starting a technical negotiation. You need to understand process capability. If your tolerance is tighter than what their machines can realistically hold, you're inevitably going to get a box of parts that fail inspection. Critical dimensions and features are typically monitored with CP and CPK requirements. CP is a process capability index and evaluates the potential of the process by measuring variation relative to specification limits, assuming the process mean is centered. A CP above 1.33 indicates strong potential for consistently meeting quality standards. Experienced mechanical engineers will work with suppliers to understand what their processes can reliably achieve. Conversations with suppliers and manufacturers should be collaborative rather than adversarial or confrontational. Adjusting geometry slightly can significantly improve yield and reduce cost. Selecting a different process like machining instead of 3D printing can accelerate prototyping even if it temporarily increases unit cost. Talk to the machinist or manufacturer early on and ask for a DFM review. They'll tell you exactly where your design is making the part expensive for no reason. Lead time, tooling investment, batch size, and ramp risk all and that's designing within manufacturing capability. Every manufacturing process has capability limits. When you send a drawing to a vendor, you're starting a technical negotiation. You need to understand process capability. If your tolerance is tighter than what their machines can realistically hold, you're inevitably going to get a box of parts that fail inspection. Critical dimensions and features are typically monitored with CP and CPK requirements. CP is a process capability index and evaluates the potential of the process by measuring variation relative to specification limits, assuming the process mean is centered. A CP above 1.33 indicates strong potential for consistently meeting quality standards. Experienced mechanical engineers will work with suppliers to understand what their processes can reliably achieve. Conversations with suppliers and manufacturers should be collaborative rather than adversarial or confrontational. Adjusting geometry slightly can significantly improve yield and reduce cost. Selecting a different process like machining instead of 3D printing can accelerate prototyping even if it temporarily increases unit cost. Talk to the machinist or manufacturer early on and ask for a DFM review. They'll tell you exactly where your design is making the part expensive for no reason. Lead time, tooling investment, batch size, and ramp risk all factor into design decisions. If If you specify a specialty titanium alloy that has a 16-week lead time for a project that's due in 8 weeks, you failed before you even started. A mechanical engineer should understand the entire global supply chain and which materials are quote unquote stock and which processes might bottleneck the entire project. Now, before we talk about the remaining skills, I want to emphasize here that no matter what it is you're designing, sourcing prototype and production parts, whether for personal, school, or work-related projects, presents all kinds of challenges. Engineering projects often face very tight deadlines, and finding the right supplier or manufacturer who can make quality, affordable parts fast and provide timely feedback is nearly impossible. That's why I highly recommend you guys to try out Jiga.io, who is very kindly sponsoring this video. Jiga is the first trust-driven custom parts manufacturing platform that connects you with a vast network of vetted suppliers, allowing you to directly communicate your requirements to them. Before Jiga, engineers only really had two options for sourcing custom parts. First were local machine shops that offer trusted collaboration and sometimes better pricing, but they would often hit capacity limits, can't take on every type of project, or just go silent when you need a quote. Second were instant quote platforms like Xometry and Protolabs that trade higher costs for speed, but there's no supplier relationship or direct communication. They're good mainly for quick one-offs and early prototyping. That's where Jiga comes in. Jiga combines the best of both worlds by providing you with direct access to vetted manufacturers with no black box to get real feedback, reliable capacity from R&D to production, and pricing that actually makes sense for professional production. Recently, I needed a custom part made for a project. I simply uploaded my CAD files to Jiga, and literally within minutes, I got competitive quotes from 3 different suppliers and received precision parts in under a week. Jiga is also trusted by the fastest growing hardware startups and top tier companies like NASA and Siemens, so you can be sure the quality and on-time delivery of your parts are guaranteed. So if you want to see how Jiga can make your next project smoother, definitely check them out through the link in the description below. Continuing on to the third skill is hardware selection and integration. The best part about industry is perhaps the massive selection of readily available commercial off-the-shelf hardware for us to choose from. You need to know how to navigate the massive catalogs of vendors like Masumi or McMaster-Carr. Why design a custom linear slide when you can buy a pre-rated high precision rail for a fraction of the cost? Using a part with a published load rating and an established failure rate is almost always better than a custom made one. This includes your fastening strategy. You need to know when to use helicoils or key inserts for threads and soft materials like aluminum so they don't strip after 3 service cycles. Understanding the difference between a shoulder bolt for precision alignment and a standard hex bolt for clamping is a basic requirement that school never mentions. Beyond bolts, intelligent selection of bearings, bushings, gears, and splines distribute load effectively and reduce stress concentrations. Choosing proven commercial components instead of custom geometry reduces risk and shortens development timelines. Now, the fourth skill is absolutely critical: tolerance stack-up analysis and geometric dimensioning and tolerancing, or GD&T. In production, no features exist at its nominal dimension and varies within a statistical distribution, as previously mentioned, for numerous reasons. Machining processes drift over tool life, injection molded parts shrink based on cooling rate, and sheet metal bends vary with grain direction and tooling wear. When an assembly contains thousands of components, dimensional variation accumulates along functional axes. To ensure variation doesn't impact performance or function, mechanical engineers might choose to perform a worst-case tolerance stack-up analysis, which assumes every single part, for example, in a 10-part assembly, will be at its absolute limit at the same time. If you design that way, your tolerances have to be incredibly tight to make sure everything fits together, and you should be prepared to pay a lot more. The preferred option is to do a root sum square tolerance stack-up analysis, which is a statistical analysis method that assumes the normal distribution describes the variation of dimensions. GD&T is just as equally important in terms of getting parts that are within specification. If you aren't using GD&T following ASME Y14.5 standards, then you likely aren't giving the manufacturer enough information to build the part, start driving up costs by over-tolerancing features that don't matter. You need to understand datum selection. Datums define functional alignment, not just inspection references. Proper geometric controls communicate design intent clearly to manufacturing and quality teams. Your datums should not be random edges, but instead the actual mating surfaces of the part in the assembly. If your datums don't match the physical constraints of the assembly, then your tolerances don't control the fit. Perhaps one of the most important GD&T concepts is maximum material condition, or MMC. This is the bonus tolerance that allows a part to pass inspection even if a hole is slightly out of position, provided the hole is large enough for the mating pin to fit. Understanding the relationship between size and position is what saves a $100,000 production run from the scrap bin, because you gave the machinist or manufacturer the flexibility the design allows. I made a whole video on GD&T that you guys can check out through the link below. Skill number 5 is simulation judgment. Everyone knows how to hit the run button in ANSYS or SOLIDWORKS, but the problem is that most people have no idea whether a model is set up properly or if the results are garbage. For FEA, if you over-constrain a model, the stress results will be artificially high and you'll waste weeks trying to fix a problem that doesn't even exist. You have to understand structural stiffness. Is the mounting bracket actually rigid, or does it flex under load? If the housing it's bolted to flexes, then your fixed constraint is a lie. Then there's vibration and thermal analysis. Most engineers skip modal analysis, but in industry, random vibration is a primary failure mode for electronics and moving hardware. If your part's natural frequency hits the same range as the motor it's mounted to, it will vibrate to pieces regardless of its static factor of safety. For CFD, ask if you're using the right turbulence model for the Reynolds number of your flow. Did you actually model the air gap and contact resistance, or just assume a generic heat transfer coefficient? If you can't justify your mesh density or wall functions, then your simulation is just a pretty picture for a PowerPoint slide. At number 6 is failure analysis. Understanding how a product fails, not just how it's intended to function, is essential to the product and company's success. You need to master failure modes and effects analysis, or FMEA. I kid you not, I've never even heard of this in university before I did my first internship. This is, in a nutshell, a cold systematic audit of every potential failure point in a product, specifically how each failure is likely to occur, be detected, and its severity. If a sensor fails, does the whole system explode, or does it shut down safely? You need to know how to look at a fracture surface and tell the difference between a brittle fracture or fatigue. A part that can hold 1,000 pounds might fail at 100 pounds if that load is applied 10 million times. Now, skill number 7 is often overlooked, and that is systems level trade-off judgment. There's no quote-unquote perfect design. There's always going to be a series of trade-offs that need to be made. If you want a part to be stiffer, it's going to be heavier. If you want a part to be cheaper, the tolerances have to be looser. If you want it more precise, then the assembly time goes up. A marketing person says, quote unquote, the product needs to be light. You have to translate that into, we need to switch from 6061 aluminum to a magnesium alloy, which increases cost by 30% and requires a different coating for corrosion resistance. If the software team needs a bigger camera sensor, then you need to figure out if you can shrink the heatsink. If not, can you move the battery? Optimizing a single component without understanding system impact can create downstream problems. Mechanical engineers who consistently consider system level consequences gain trust and responsibility more quickly. Last but not least, skill number 8 is execution discipline. What do I mean by this? Engineering projects typically end when a validated product ships on schedule, and that requires structured workflow, documentation control, and relentless follow-through. It's not just about designing good parts, but knowing how to move those parts through a company's workflows. You need to understand version control, design revisions, and engineering change orders or notices. Knowing how to check in files, generate part numbers, and get drawings approved is what keeps a project from collapsing. Then there's the communication aspect. There's going to be team members, stakeholders, and customers that are more difficult to work with, so you need to deal with them differently. You'll have senior machinists who think you're your designs are overcomplicated, or project managers who can't understand why a quote-unquote small change in a whole location requires 2 additional weeks of revalidation. What I learned is you need to win arguments with data. Show the FEA or stack up results. Perform a cost-benefit analysis. You need to learn to talk risk with managers and tooling with manufacturers. I view communication as a technical tool, and if you can't explain why a design choice was made, that choice is going to be overridden by someone with more seniority but less data. Now, to conclude, mechanical engineering education builds the knowledge and skills needed to understand how the physical world behaves. That foundation is indispensable. However, success in industry depends on integrating those things with manufacturing constraints, statistical variation, system trade-offs, supplier capability, and disciplined execution. Only when these skills are mastered can a mechanical engineer design products that meet specifications, that scale, that launch on time, that meet cost targets, and survive in the field. Remember, your degree opens the door to opportunities, but these skills determine how far your career advances beyond it. All right, guys, that's it for today. As always, thank you so much for watching. If you found this video helpful, be sure to check out my video here where I talk about several things that helped me master tolerances and GD&T, and I'll see you in the next one. Peace. In mechanical engineering, few concepts appear more straightforward on the surface, yet are more misunderstood in practice than tolerances. In school, we're taught how to dimension parts on drawings and CAD, and barely any emphasis is placed on tolerances. In industry, tolerances affect just about everything you can think of, from manufacturing costs, inspection times, and scrap rates to product performance and even customer satisfaction. Over a span of 4 years, I've developed products from iPhones to automatic flush valves, soap dispensers, and hand dryers, where space is very tightly constrained and tolerances tend to make or break designs. So in this video, we'll break down the fundamentals of tolerances, clear up any common misconceptions, and illustrate how tolerances can improve our designs and effectiveness as mechanical engineers. We'll cover traditional dimensional tolerances, how to strategically assign them, and how geometric dimensioning and tolerancing, or GD&T, provides a better, more realistic framework for defining part requirements. There's also a game-changing tool, Giga.io, that has totally changed the way I design and make parts that I'm excited to share with you. So let's get started. Let's begin with the basics. No part is ever manufactured to its nominal size. There will always be some deviation, and tolerances define how much variation is acceptable without affecting the function of the part. For example, if you have a shaft with a diameter of 50 millimeters, it might be acceptable for it to be between 49.95 millimeters and 50.05 millimeters. That plus minus 500ths of a millimeter is your tolerance. Where most engineers go wrong is assuming tighter is better. They assume a tighter tolerance means higher quality and better performance, but there's a huge trade-off. Tighter tolerances require more precise machining, better tooling, slower feed rates, and more frequent inspection. That means higher costs, longer lead times, and increased difficulty in sourcing. Over-tolerancing is one of the most common causes of cost overruns and supplier complaints. So let's say we're designing a plastic housing that mates with the cover. If you assign a 500th millimeter tolerance to all the screw holes and snap fits, you're implying that extremely high accuracy is required. But plastic injection molding can't hold those tolerances reliably, especially for larger parts. The mold, the material shrink rate, and temperature all introduce variation. Ideally, these features should have a more relaxed tolerance of plus minus 2/10 of a millimeter if possible. So how do you assign the right tolerance? Start by thinking functionally. What does the feature do? Is it aligning a shaft in a jet engine carrying 300 soles? Is it locating a connector in a smartphone? Or is it creating a seal in a medical device? Determine how much variation variation that function can tolerate and assign a tolerance accordingly. Collaborate with your manufacturing team or suppliers if needed. They can definitely give you insight into what can be held easily and what might require additional processing. Moving on, there are three main types of fits in mechanical design: clearance, transition, and interference fit. In a clearance fit, there's always space between parts, such as a shaft and a hole. A transition fit may result in either a small clearance or interference. For an interference fit, the parts are designed to press against each other and require force to assemble. Now, let's talk about dimensional tolerancing versus geometric dimensioning and tolerancing, or GD&T. In traditional dimensional tolerancing, you define the X and Y position of features with linear dimensions and assign tolerances like plus minus 1/10 of a millimeter to them. This creates a square tolerance zone. For a hole, that means the center must fall within a square box that is 0.2 millimeters wide. But a square zone doesn't make sense for a round hole. The result is a tolerance that is both overly restrictive in some directions and too loose in others. GD&T actually solves this by allowing you to control tolerances in a way that reflects the intended function of the part or assembly, such as using a circular or cylindrical tolerance zone. Tolerances are applied to features like holes, surfaces, or edges rather than dimensions. Feature control frames are these compartmentalized boxes used to fully define a geometric characteristic. The first box includes one of the 14 geometric characteristic symbols, such as position, flatness, and parallelism. These 14 characteristics can be split into 5 categories: form, orientation, location, profile, and runout. The second box contains the tolerance value, often with a symbol indicating the shape of the zone, like diameter for true position of a circle. I like to think of the tolerance as a 3-dimensional tolerance zone that surrounds the true position. The following compartments specify datum references listed in order of precedence. It's very important to define your datum reference frame carefully. It establishes the origin and orientation from which other features are controlled. Always include clear datum symbols on your drawing to align with the GD&T frames. Now, it's worth mentioning a modifier can be added behind a tolerance or datums. GD&T modifiers are symbols placed in a feature control frame to clarify how a tolerance is applied. The most common is maximum material condition, or MMC. Under MMC, the tolerance applies when the feature contains the most material. For a hole, this is the smallest diameter. For a pen, it's the largest diameter. The great thing about MMC is it allows bonus positional tolerance as the feature departs from its MMC size, making parts easier to manufacture and inspect. Now, before we continue talking about GD&T modifiers, I want to emphasize here that no matter what it is you're designing, sourcing custom parts, whether for personal, school, or work-related projects, presents all kinds of challenges. Engineering projects often face very tight deadlines, and finding the right supplier or manufacturer who can make quality, affordable parts fast and provide timely feedback is nearly impossible. That's why I highly recommend you to check out Jiga.io, who is very kindly sponsoring this part of the video. Jiga is a unique custom parts manufacturing platform that connects you with a vast network of vetted suppliers, allowing you to directly communicate your requirements to them. This means you get parts faster, cheaper, and made exactly the way you want. With Jiga, you get to build relationship with suppliers, which not only makes the process more reliable, but also simplifies even the most intricate projects. Whether you need prototype or production parts, Jiga can do it all with its CNC machining, sheet metal, 3D printing, and plastic injection molding capabilities. Their platform is insanely user-friendly. All you need to do is upload your parts, and Jiga will provide a quote within hours from multiple suppliers, allowing you to compare prices and lead times to get the best deal possible. What's even better is Jiga's service is fully transparent. You can directly communicate with the supplier for DFM feedback on Jiga's website and add notes to the 3D models to let them know your requirements. Recently, I needed a last-minute custom part made for a personal project. I simply uploaded my CAD files to Jiga, and literally within minutes, I got quotes from 3 different suppliers and received the parts in under a week. Jiga is also trusted by top-tier companies like Google, NASA, and Flex, so you can be sure the quality and on-time delivery of your parts are guaranteed. So if you're looking to simplify simplify and streamline your manufacturing and get parts much faster, definitely check out Giga.io through the link in the description below. The second modifier we'll talk about is least material condition, or LMC. Under LMC, the tolerance applies when the feature contains the least material. LMC is useful for features where strength or clearance is a concern at minimum size. The third and last modifier we'll talk about is regardless of feature size, or RFS. RFS is the default and applies if you don't include a modifier. This means the tolerance must be met regardless of the actual size of the feature. There's no bonus tolerance here, and it's the strictest interpretation. So to give an example, suppose we have a metal bracket with a mounting hole, which is considered a feature of size. The hole diameter should be called out with the dimensional tolerance. In this case, it's a unilateral tolerance. This means the hole's diameter can range from 10 millimeters to 10.05 millimeters. The MMC for the hole is 10 millimeters because that's when the hole is the smallest and contains the most material. The position tolerance is called out in a feature control frame. The position of the hole center must fall within the tolerance zone of 0.20 millimeters when the hole is smallest, or at MMC. But if the hole is made larger, say 10.03 millimeters, you gain bonus tolerance. The bonus tolerance is calculated as actual hole size minus MMC size, which equals 10.03 millimeters minus 10 millimeters. That's 300ths of a millimeter, which gets added onto the true position tolerance of 0.20 millimeters. This eases manufacturing and inspection while still meeting functional fit requirements. The same can be applied to LMC, which is useful if you want to control, say, the position of a hole near an edge. Now, I won't be going into each and every geometric characteristic in this video. If you want to learn more, I highly recommend you to check out the website GD&T Basics that covers everything you would ever want to know about GD&T with some great examples. I'll drop a link in the description below for you to check out. However, I do briefly want to cover true position because it's one of the most useful and complex out of all the GD&T symbols. Position may be applied to any feature of size like a hole, slot, boss, tab, or sphere, and control the central elements of these features. For a hole, this would be a circular area around the nominal location where the feature must fall. The tolerance zone would be cylindrical and extend through the thickness of the part. The entire feature axis, midplane, or point would need to be located in this tolerance zone. GD&T gives manufacturers greater flexibility while maintaining function, and as a result can reduce part cost. Remember, GD&T is not meant to replace dimensional tolerancing, but rather complement it and highlight which aspects of your design are the most critical. One common misconception is that GD&T is only for aerospace or high precision applications. That's just not true. In reality, GD&T can and should be used whenever the function of a part depends on geometry, especially in assemblies. However, whether you can use GD&T depends entirely on your organization. Sadly, not every company implements GD&T. Now, generally speaking, most drawings will have a general tolerance block that governs all unspecified dimensions. Then you only need to explicitly define tolerances for critical to function features where fit, alignment, or performance depend on tighter control. Another mistake that engineers make is ignoring tolerance stackups. Leveraging tolerance analysis tools in your CAD software or performing a worst case or root sum square analysis can help you predict stack-up issues before they become expensive problems. Tolerances also influence inspection. If your part drawing includes hundreds of unwarranted tight tolerances, the inspection process becomes way more complex, time-consuming, and costly. One way to reduce cost and inspection burden is to define general tolerances for non-critical dimensions following ISO 2768 or a similar standard. Reserve tighter tolerances and GD&T callouts to features that are essential to performance and function. I've also seen many engineers fail to update tolerances when the design changes. For instance, they might resize a feature in CAD but forget to update the associated tolerance or revise the drawing. This creates a mismatch between design intent and actual actual manufacturing expectations. Always validate your drawings against the latest CAD model and review tolerances after any design change. Now, I want to mention here that one thing I always do is test designs physically before they ever go into production. 3D printing is my go-to for catching design issues, checking assembly fit, and actually feeling how parts work in my hands. Lately, I've been using this printer, the FlashForge 85X, in my own workspace to make functional parts, prototypes, and proof of concepts. It can print a part in 4 colors and in a wide array of materials, including PLA, ABS, ASA, even flexible materials, and does it fast, up to 600 millimeters per second, with the precision to hit tight tolerances. That means I can check for fit and function before spending thousands of dollars on tooling. I'll often print a few variations of a part, measure and test them, and instantly know if I need to tweak the CAD model. This quick feedback loop saves me from expensive mistakes later. Whether it's a side project or something headed for production, having a 3D printer closes the gap between theory and reality a lot faster. And just to be clear, this isn't sponsored. A 3D printer is an essential tool that every engineer should have to streamline the design and product development process. I'll drop a link for the 85X in the description below for any of you who are interested. Now let's briefly go over decimal precision. Many engineers confuse the number of decimal places with accuracy. A dimension with 1 decimal place like 10.0 millimeter generally implies a looser tolerance, such as plus minus 5/10 of a millimeter. 2 decimal places like 10.00 millimeters suggest plus minus 1/10 of a millimeter, and 3 decimal places imply tighter control, such as plus minus 1/100 of a millimeter. Never assume tolerances just by the number of decimal places, and always specify them clearly. Tolerances also impact cost differently depending on the manufacturing process. But keep in mind that tolerance capability is a function of material, machine condition, and feature size, so talk to your supplier or manufacturer about what tolerance ranges are realistic for your specific part. For small parts, maintaining tight tolerances is relatively easier because the effects of tool deflection, thermal expansion, and fixturing errors are minimal. In large parts, especially in casting and machining, these factors amplify, and holding tight tolerances is harder and more expensive to achieve. That's why the same plus minus 0.1 millimeter tolerance on a 10 millimeter gauge is reasonable, but on a 1 meter long structural beam, it's much more challenging. Now, I'll end by saying tolerances reflect our understanding of a product's function, how it's manufactured, assembled, and inspected. Every tolerance that you apply is a decision that affects time, cost, quality, and reliability. The goal isn't to make everything as accurate as possible, but as accurate as necessary. Learn how tolerances affect the entire product lifecycle by talking to machinists, other engineers, and manufacturers. That's when tolerances will make the most sense. All right, guys, that's it for today. As always, thank you so much for watching. If you found this video helpful, be sure to check out my video here, where I discuss why you might not truly understand mechanical engineering yet, and I'll see you in the next one. Peace. In university, you take a computer-aided design class that asks you to model this part based on its 2D drawing in SOLIDWORKS, Creo, or whatever CAD software your school uses. And while there are a million different ways to constrain features, define relations, build your models, and still arrive at a visually correct result, there's only a handful of methods that actually reflect proper design intent. It's these nuances and subtle differences that schools don't teach, and what separate a great mechanical engineer from a mediocre one. In my experience, many fresh grads and even experienced mechanical engineers are oblivious to good design practices and proper design intent, which leads to a lot of unneeded frustration, massive project delays, and budget overruns throughout the product development process. A lot of design mistakes don't show up until you're deep into manufacturing, testing, or assembly, and basically when it's too late and expensive to fix. So in this video, I want to walk through the most common design mistakes that I see engineers making and how you can avoid them in your designs and projects. The first category of mistakes is design intent and CAD best practices. These are mistakes that affect how your CAD model behaves, rebuilds, and evolves when dimensions are modified. Mistake number one is poor feature referencing. If your entire model or assembly falls apart or crashes every time you go to update a feature, then there's probably no design intent baked in. So one of the simplest examples I can give is how you create and dimension a hole in a block. The hole can be a certain distance from a corner or edge, or it can be in the middle of the face. There's really no right or wrong answer. It completely depends on what the hole needs to do as the design evolves. If it has to stay centered no matter the size, constrain it to the midpoint. If it needs to be fixed a certain distance from the edge for a screw or connector, dimension from the edge. The key is to match your modeling to your design intent. You really need to anticipate how your design will change in the future and define dimensions and relations based on that. Avoid anchoring features to center lines and features like edges that might move or disappear later. Remember to use construction lines, patterns, and mirror features to keep things consistent and smart. The second mistake is an extension of the first one, and it's not incorporating parametric thinking. Hard coding dimensions everywhere makes your part fragile and tedious to update. Use global variables, linked values, and equations so your designs can adapt and scale as requirements change. To give an example, imagine you have a 100 by 60 millimeter plate. You draw each hole and dimension it manually, 10 millimeters from the X edge and 10 millimeters from the Y edge, and you call out the diameter. That's 3 dimensions per hole. If you later want to change the plate to say 150 by 90 millimeters, you have to edit 12 dimensions manually. Instead, the preferred way is to set global variables, so plate length equals 100 millimeters, the plate width equals 60 millimeters, the edge offset equals 10 millimeters, and the hole diameter equals 5 millimeters. Then sketch the plate and link the dimensions to the global variables we defined, plate length and plate width. Next, we can create holes by sketching a hole in the top or bottom corner. Link it to the global parameter hole diameter and constrain its position with the global variable edge offset from the X and Y edges. Then draw 2 center lines through the midpoint of the plate. Mirror the circles about both center lines to get 4 symmetrical holes. Now, if the plate size changes or you want to shift the holes to 15 millimeters from the edges or change hole size, just change the global variables and equations, and the whole design updates automatically. Now, in the following example, one hole is fixed, one is driven by an equation, and the other 2 are mirrored. As the size of the hinge changes, the holes remain properly spaced along the length and width. Now, when you're designing real products like an iPhone, jet engine, or a car, there's going to be hundreds, if not thousands of parts and hundreds, thousands to millions of dimensions, relations, and constraints. Failure to account for design intent from the start will make your life hell down the road. Your model will behave unpredictably every time you go to update because it wasn't built with the underlying purpose or constraints in mind. Mistake number 3 is overdefined and underdefined sketches. A sketch that is arbitrarily locked down or left floating is going to rear its ugly head during rebuilds. Use meaningful constraints like equal length, concentricity, and symmetry that reflect how the part should behave. A well-defined sketch should have just enough constraints to reflect your design intent. Now, if we only dimension one side of a rectangle, it's underdefined. And if you drag a corner, it moves and is unstable. Overdefining is when you, for example, dimension both sides and then you set both sides equal. Now the software is confused. Should it be a square or rectangle? Mistake number 4 is neglecting feature tree organization. A messy feature tree is just just like bad code. It works until you need to go edit or debug it later. The feature tree is essentially your parts timeline. It records every sketch, extrusion, cut, fillet, hole, draft, and pattern in the order they were created. So many engineers add features out of order, use poor naming conventions like Boss Extrude 37, and include random unnecessary sketches and broken features. It really becomes a nightmare when you or someone else revisits the file weeks or months later. To have an organized feature tree, it's best to rename features such that your tree is readable at a glance. Use self-explanatory names like boss, main body, cut USB slot, and sketch mounting holes. To prevent catastrophic rebuild errors and getting locked out of editing core shapes, it's critical to model features in a specific and logical sequence. First, you want to model base features, whether using boss extrude, revolve, and or sweep and lock functions. This is the foundation of your model. Everything else is built on or removed from this shape. If you get this wrong, the entire model becomes unstable. Second, you want to work on major additive and subtractive features like shells that hollow out the body, bosses, ribs, flanges, and any large cutouts. These features define the functional geometry or the space needed to meet mechanical or space requirements. Adding them early allows you to draft, pattern, or manipulate them before any fine detail work begins. Third, include drafts to faces, features, and extrusions in your part if there are any. Drafts are required for manufacturing processes like injection molding and casting, so the part can be ejected from the mold. So you want drafts before any detailed features like holes or fillets to prevent geometry distortion, keep rebuilds clean, and avoid broken edges from downstream references. Fourth are holes, counterbores, pockets, slots, notches, etc. These are functional details that rely on the core geometry. Adding them after drafts ensures that faces and edges are final and won't shift due to molding considerations. Next, add any feature patterns, be it holes, cuts, bosses, or pockets, after you've perfected the things you are duplicating. Last but not least are cosmetic features, including fillets, chamfers, edge breaks, screw threads, logos, and text emboss and debosses. Save the pretty stuff for last. Applying things like fillets too early can make downstream features harder to sketch on, cause face ID changes and broken references, and complicate shelling, drafts, and cuts. Now, the second category of mistakes is design for manufacture and assembly, or DFMA. As the name implies, these mistakes make the design harder, slower, or more expensive to manufacture and assemble. Now, DFMA is massive. It's a whole philosophy that touches every aspect of product development, but I'll try to cover some of the most common mistakes that engineers make in this video. The first mistake is ignoring tolerances. Too many engineers either leave default tolerances from the title block and assume they're good enough, or slap on 10,000ths of a millimeter or very tight GD&T symbols. This leads to parts failing inspection despite being functionally okay, skyrocketing costs due to tight machining or inspection requirements, delays and redesigns when parts don't fit together on the assembly line. There are different tolerance standards like ISO 2768 and ISO 286 for fine, medium, and coarse tolerance classes that serve as a good starting point. You want to assign tolerances based on functional requirements. Only give tighter, appropriate tolerances to critical features like press fits or alignment holes. For non-critical features like aesthetic cutouts or logo areas, call out looser tolerances to save money and time. For every dimension, ask what happens if the feature is half a millimeter off. If the answer is nothing, loosen it more. Be sure to collaborate with machinists, suppliers, and leverage tolerance analysis tools in CAD to validate stack-ups. If we look at this graph for CNC machining, costs go up exponentially as tolerances are are made tighter. Also, another point I want to make is that the old-fashioned way is to slap plus minus tolerances on every dimension. There's nothing wrong with that, but it creates a square tolerance zone, which doesn't make sense for holes because they're round. Why should their centers be combined to a square? This drives up manufacturing costs without improving performance. To solve this, geometric dimensioning and tolerancing recognizes this problem and introduces a type of tolerance called true position, which allows for a three-dimensional circular tolerance zone and can therefore lead to a part being cheaper to manufacture. I'll very likely make a separate video about tolerances in the future because it definitely deserves one. Now, before we continue, one of my favorite platforms that was essential in teaching me how to think like an engineer was Brilliant, the sponsor of today's video. It helps you get smarter every day with thousands of hands-on lessons in math, physics, data analysis, programming, and AI. Brilliant breaks down problems using a first principles approach. Their lessons develop problem-solving skills by allowing you to experiment with concepts. This method is proven to be 6 times more effective than traditional lecture-based learning. Brilliant's lessons are crafted by professors, researchers, and professionals from MIT, Caltech, Microsoft, and Google, so you learn from the best. Brilliant promotes critical thinking through active learning, not memorization, so you become a strong problem solver. It also helps promote the habit of daily learning, essential for both personal and professional growth. Brilliant's interactive bite-sized lessons allow you to learn on the go and make the most of your time. One of my favorites is Brilliant's scientific thinking course that teaches you to think like an engineer as you design gear systems, bridges, and electric circuits. To try everything Brilliant has to offer free for a full 30 days, visit brilliant.org/engineeringgonewild or scan the QR code on the screen, or you can check out the link in the description below. You also get 20% off an annual premium subscription. Now, mistake number 2 is forgetting about manufacturing constraints. You can design anything in CAD, but it's useless if it can't be made. Engineers often create features that look fine in CAD, but are a nightmare to machine, mold, or fabricate. Common offenders include sharp engineers often create features that look fine in CAD, but are a nightmare to machine, mold, or fabricate. Common offenders include sharp internal corners, which concentrate stress and are difficult to manufacture because most tools, like end mills, are round. Then there's deep, narrow holes that are very hard to drill, cause chatter, and can lead to tool breakage. Undercuts and injection molding, casting, and even CNC machining require special setups and tools like side actions and T-cutters. Then there's impossible tool paths for CNC machining due to very tight spaces or steep walls and designs. Each manufacturing has an extensive set of rules and best practices that you should follow. But in general, all your designs need to respect the constraints of processes, tooling, and materials. Mistake number 3 seems obvious, but you'd be surprised by how many engineers commit it, and that's using non-standard hole sizes and fasteners. Designing a 4.3mm hole that requires a custom drill bit or using 23 different screw types across a product makes manufacturing, sourcing, and assembly a pain. Depending on the application, choose a limited fastener family if you can, like socket head cap screws between M3 to M6 range. Also ensure that holes match fit type standards like clearance, tap, and press fit. Mistake number 4 is simple but overlooked: disregarding tool access or assembly clearance. If a screwdriver, socket, or torque wrench can't reach it, it's not going together. Design with the assembly sequence in mind and add enough clearance for the tools that your technicians will use. Mistake number 5 is the parts have no locating features or requires too many hands or fixtures to assemble. If it takes 3 people in a custom jig to hold parts in place while tightening bolts, then that's a bad design. Aim for self-locating parts and designs incorporating pins, bosses, tabs, or other features that give the assembler a way to put parts together quickly and accurately. Lastly, mistake number 6 is your part can't be disassembled for repair or maintenance. Add access panels, modular sub-assemblies, and captive screws so the product lives longer and is easier and cheaper to service and maintain. Now, I'll close by saying that I hope this video is able to help you avoid all of these design mistakes and streamline your engineering engineering projects. When designing, the devil is in the details, and one bad assumption or overlooked constraint can delay a project by weeks and cost thousands of dollars to fix. Alright guys, that's it for today. As always, thank you so much for watching. If you found this video helpful, be sure to check out my video here where I talk about how I doubled my engineering salary in 3 years, and I'll see you in the next one. Peace.
Rebola, mexe, deixa o som entrar. Todo mundo junto, ninguém vai parar. O batidão não vai parar. Sente a energia no ar. Vem brilhar.
А стадионе что будет? Где люди сидят?
Трибуна. Что у него, проспорт, что ли, все?
У этого что было? У этого... Нет, как его зовут? Суфьянова же это... Нет, другой! На берегу этот...
Давай дальше другой делай.
Тут слово даже не знаю. Подожди.
На берегу что там было? Закат.
Каспийское?
Море.
Нет, другой. Каспийское?
Груз.
Нет!
Озеро.
Каспийское?
Озеро.
Нет! Ну вот это.
Рио-де-Жанейро, что?
Нет. Время!
Что немаловажно, очень много спарринг-партнеров. Даже именно моего веса много спарринг-партнеров.
Хабиб, милый. Хабиб, милый. Приветствуем тебя. Скажи, пожалуйста, бой состоится с Флойдом? И ты ММА или бокс?
Я думаю, что я больше сфокусирован на ММА.
Хабиб, когда ты будешь драться с Конором?
Ассаламу алейкум, у меня вопрос к Хабибу.
Дядя Хабиб.
Вопрос к Хабибу.
Ассаламу алейкум.
Ассаламу алейкум, Хабиб. Хабиб.
Хабиб.
Ассаламу алейкум, Хабиб. У меня к тебе два вопроса.
У меня к исламу тоже вопрос. Идеально, как бы для тебя прошел бы следующий год, 2020, как бы ты его хотел бы провести, какие соперники ты бы выбрал бы себе поочередно, так скажем, начало года, середина и конец. Ну, как у фанатов у меня к нему вопрос.
Не знаю даже, я хотел бы уже, у меня уже серия побед из 6 боев, и никто из десятки не принимает бой, никто не хочет драться, я уже думаю, Хабиба может вызвать сразу. Что смотришь?
Постоянно ты закрываешь и даешь себя бить.
Keep fighting with me same night in UFC 187. 2 or 3 days in the week, you need very hard sparring. Like today, when we go to the cage, opponent no go like is enough. We understand this is sport, and if you need win all the time, you need hard sparring. After sparring with brother. Заряженный, отвечаю, Жойс. Ислам-то спал, я до утра как будто не спал, Жойс. Думал об этом. Вообще, перед своим боем сплю, Жойс. За 2 часа до боя тоже. Когда братья дерутся, тяжко бывает.
Hey, why you guys always cheating? Like both of them, like you, a lot of bullshit people inside the house. Why? Get out of here. Get out of here.
Oh my God!
This is my glove, you see.
Brother,
No,
this
it's
is
mine.
Islam. No, brother, this is Islam
This is-
gloves.
This is
Look,
my
this
glove.
is Islam glove. Look what he did.
No, this is this. Who's this guy? Can't take two hands.